Okay, let's begin. So we are working on 7.7, approximate integration. And of course, as I was explaining last time, the idea behind this section is that there are some functions that you cannot integrate very easily, but sometimes you want to be able to find an answer. And there are certain situations in which we can find an answer to as good an approximation as we want. So that's if we have a definite integral, so our integral is contained in some bounds, and you want to figure out a value for that integral. Turns out we can, by just going sort of back to first principles, sort of going back to that Riemann sums idea of computing an integral, we can figure out essentially the area under the curve or whatever that might relate to. So we have a bunch of methods here. There are many more methods, but in calculus 2, these are the typical methods usually covered. I feel like the right-hand and left-hand rule would have been things you've seen before last year.
Yeah.
Right? So like towards the end when you were talking about the integral for the very first time, when they introduced the idea of a Riemann sum, they probably showed you how to set up rectangles starting from the right. Well, we're adding to that. Did you guys do the midpoint rule as well?
Yeah, we did that.
But trapezoid, no. Trapezoid and Simpson's, no. So, okay, so for the most part we're familiar with this. And as I said, usually I have this whole spiel about how to sort of remember the formula and intuitive reason why this is so, but I'll be giving you guys the formulas so you don't have to memorize them or anything. Just know how to use them, because I really don't see the point in memorizing them, actually. But since I'm writing your final and everything, then I can put whatever I want on it. So I'll just put like a little formula section with this stuff there. So yeah, for the most part then, since you guys already sort of have an idea of what's going on, let's actually just jump into it. Did you guys learn about the error formulas last time?
We could use a refresher, probably.
What?
We could use a refresh, probably, on
Yeah.
understanding the concept.
So the idea is there's a difference between your actual answer and the answer that your approximation is, and that's called the error, and this guy measures that. We'll get to that pretty soon, but let's actually, I think we can just jump into a problem and do some approximations. So on the second page, we'll go to the problems. There are 4 problems set up here. The first one is an integral that you could do. Right, so that, and then you can, so in 1 and 2 you can actually find the answer and actually compare how well we're doing according to this approximation. But the last integral, for example, is one that we can't integrate, so we kind of have no choice there. So yeah, let's talk about the integral 0 to pi of sine x. So I want you to approximate this value. It is a value that we can find, but I just want to illustrate the point to you. And I figure it's nice to have an integral where you can actually go and find the values and actually check up how good our approximations are. So we're going to do this integral. I'm going to use n equals 4. So I can say n equals 4, or I can say 4 subintervals. These are both describing the same thing. And I want you to approximate this integral with 3 rules, the midpoint rule, so a little bit of a refresher there, but we're also going to apply the trapezoid rule and Simpson's rule. Okay, and just a little bit of notation here. Midpoint, yeah. When we're saying, just some notation, just in case I write it down, I want you to know what I'm talking about. So if given n subintervals, if I use the right-hand rule, I would call that, say, r sub n would be the right-hand rule approximation, right? So I might just use that notation. R sub n equals blah. So, or left-hand rule, L sub n, midpoint rule. I'll use M sub n, trapezoid rule. And your textbook uses this notation as well. They use T sub n and Simpson's rule. Use S sub n. Although, which uppercase S, because we'll actually use lowercase s sub n for something else. So in other words, what I'm asking you to find here is find M4 for this integral, and find T4 for this integral, and find S4 for this integral. Okay, so I might use that notation to describe it as well. So that's just a notational kind of thing. Let's actually start with A. Right, so you have the formula there for the midpoint. How do you actually apply it here? What was the first thing you guys did when you were setting these guys up? Yeah?
I would find delta x by dividing the interval by n.
Sure. So we know that so 1, find delta x. And we have a formula for that. Delta x is equal to b minus a over n. Right? Where b is, I have that listed in a blurb in like the first paragraph of this handout. So b is the right endpoint. A is the left endpoint. And n is the number of subintervals. So you can find your delta n. So in this case, what is our delta x here? Pi minus 0 over 4. So that's just pi over 4. Okay, so after we find our delta n, what is the next thing we find? What's the next thing you look for?
The height at each of these?
Yeah, how would we figure out the height of each one?
F of pi, like each.
F of all the values. So the next thing I would find is all the values, right? Because we already know what our f is. Our f here is just going to be sine x in that formula. So that's our f of x. But we need to know what are we plugging into the f of x to find the corresponding heights. So what I would like to find here is find they call them xi because they'll number them. Here's your x1, your x2, your x3. Find the xi. I like to do it, there are many ways you can do this, but I like to actually just draw a picture of the interval and cut it up and then add them up. So here I have 0 to pi. I know I'm cutting it into 4 equal pieces. And I know each piece, what the delta x is, it tells you the length of each piece. So I know the first one, I just start at the left endpoint and add pi over 4. Add pi over 4 again. Add pi over 4 again. Add pi over 4 again. So that would be my subintervals. So each time here, I'm adding, so this is 0 plus pi over 4, and I keep adding pi over 4 plus pi over 4. You keep adding the delta x until you get to the end. So you have 4 subintervals, so you start at the left endpoint, you add the delta x 4 times, that gives you all the pieces. Now, in part A, we're looking for the midpoint rule, so what are we actually after here? Yeah?
Like points in between each of us.
Literally the points in between, the points in the middle of each of these intervals. So for the midpoint rule, you have to find another set of numbers. So we're going after the numbers in the middle. Now there are a couple ways you can get to this quickly. You can find the first one just by finding the average of the two numbers. Right? So you take 0 plus pi over 4 all over 2. And that will give you the first one is pi over 8. And you can continue doing the average of all the numbers to get the middle, but just remember that they will actually have the same spacing. So instead of doing that, you can just keep adding pi over 4 over and over again on the red ones. And to make it nicer to add to pi over 8, just think of pi over 4 as 2 pi over 8, for example. So pi over 8 plus 2 pi over 8 is 3 pi over 8, plus 2 pi over 8 is 5 pi over 8, plus 2 pi over 8 is 7 pi over 8. Right? So again, you can just think of adding that pi over 4, adding it to each one. And so now we can plug into our formula. So 3, and I'll plug into formula. We know that M4, for example, is, this is going to be delta x times f of x1 plus f of x2 plus f of x3 plus f of x4, where the x1, x2, x3, x4 represent the midpoint values. Usually when we're talking about the midpoint rule, they represent these, they call these the x1, the x2s, and these they call x1 star, x2 star, x3 star. So that's also a notational thing. So with the midpoint rule, they'll put a little star here to emphasize that we're not using the actual x values that we calculate, we're using the ones in between them. Okay? And that's basically it. So now you just plug into this formula. So your delta x is going to be pi over 4. And now you're going to have f of pi over 8 plus f of 3 pi over 8 plus f of 5 pi over 8 plus f of 7 pi over 8. Which in this case your f is just sine. Now you're allowed to use calculators on your exam, so you could actually just plug this into a calculator and say what that's approximately equal to. But if you're finding this by hand, could you do it? Do we know how to find sine of pi over 8? Do you remember? How would you find something like sine of pi over 8? Ideas. It's actually something you can work out by hand. Any ideas on how you would do that?
Is it sine pi over 4 divided by 2?
Okay, you think of that as sine pi over 4 divided by 2. How does that help you?
So you got square root of 2 over 2 over, oh. Well, sine pi over 4 is square root of 2 over 2.
Sure, but we don't have pi over 4. What does that remind you of?
Half angle.
Reminds you of a half angle formula. We know of sine of x over 2, right? What would that actually give us, the half angle formula? The half angle formula is just the reverse of the double angle formula, right? So if we had, say, sine squared, what could we write that as in the double angle formula? 1 minus cosine over 2. So I can solve for the sine. So this is plus or minus that guy. Where in this case, the plus or minus would depend on the quadrant that the angle ends up being in. So the idea is, if I replace this angle with x over 2, then that angle 2x just becomes x. And that gives you the half angle formula. I know pi over 8 is in the first quadrant, so I know it'll take the positive radical here. So it's 1 minus cosine of x all over 2. So you could actually compute sine of pi over 8 by just taking the radical 1 minus cosine pi over 4 over 2. This one you actually know from that table you memorized, so you can plug that in and you can get a nice answer in radicals. right? Once you can find sine of pi over 8, these other ones won't be that bad. You just do that thing where you cut up the circle into 8 pieces and count off the quadrants. And the only thing that's going to change on them is the signs, whether it's plus or minus, and then everything. But that's how you could have done it. But you would be allowed to plug that into your calculator and get a nice answer there. Well, a decimal answer. And I'll tell you, find it to 3 decimal places or whatever. So let's go with B. Let's go with the trapezoid. Let's find T4 for this integral. Now, as a process, nothing changes. Literally, the only thing that's changing is the formula that you're plugging it in. The end point is going to be is that these answers that you're getting for each of these different approximation methods, they will be slightly different because depending on the function, one might be more appropriate than the other in a shorter amount of time. And the point of problem 2 is for us to figure out, in this case, which was the best approximation. We're going to compute the errors for each of these afterwards. So it's the same thing. So if you were given this problem and I said, by the trapezoid rule, give me the trapezoid rule approximation with 4 subintervals. You do the same thing. The first thing you do is you find delta x, which in this case is pi minus 0 over 4, which is pi over 4. The second thing you would do is find the xi's. So 0, pi, you already know what these guys are going to be. It's going to be your pi over 4, your pi over 2, your 3 pi over 4. And now you're going to plug these into the formula. So the trapezoid rule is this formula over here. Right. Now, by the way, I want to, as I listed down here, you'll notice that some formulas start with x1, whereas some formulas start with x0, and so on and so forth. I just want you to be aware that x0 is always going to be the first guy, where this is x1, and we count up from there. So we always start at x0. The formulas, as I have them set up here, x0 is representing the A. And xn, this guy is your x4, which in this case is your xn. That always represents the B. So I just want to be clear on that. So you'll notice, for example, in the right-hand rule, you actually don't start with x0, you start with x1, because you start with the right side of the integral. Right? But in the trapezoid rule, notice that you start with x0. So we're starting with the end point here. Okay. So third thing is now we're going to plug into that formula. T4 is going to be equal to, we know it's going to be delta x over 3 over 2. Because you're using that trapezoid area formula. Half the distance of between the two parallel. Half the sum of the lengths of the two parallel sides times the distance between them. And we're literally plugging in all the x values here. So we're going to plug in f of 0, f of pi over 4, f of pi over 2, f of 3 pi over 2, 3 pi over 4, f of pi. So this becomes pi over 8. Let me just write down now. Sine of 0 plus sine of pi over 4 plus sine of pi over 2 plus sine of 3 pi over 4 plus sine of pi. These guys are actually not so bad, I think, so let's actually just do this. Sine of 0 is? 0. Sine of pi would also be 0. What's sine of pi over 4? Radical 2 over 2. Sine of pi over 2? 1. Sine of 3 pi over 4? It's again radical 2 over 2. So I have 2 radical 2 over 2, so it just gives you a radical 2 over 2. So this is really just pi over 8 times 1 plus radical 2. Right? right? And that will be my approximation for that integral, according to the trapezoid rule. Sorry. We're adding the sides. The twos go in the middle of all of these. So that would become that. Basically, you double the answer. So I can take pi over 4. Let's do C. Simpsons. Now this one is kind of weird because you have an alternating 4 and 2 in the formula, but that kind of comes from the polynomial interpolation. But you'd start the same thing, so let's just go through the motions again. The first things, so we're going to find S4. First thing you do is you find your delta x. It's b minus a over n, pi minus 0 over 4, which is pi over 4. 2. Find your xi. Here that's 0. We know we're cutting into 4 pieces, that's pi over 4, pi over 2, 3 pi over 4, 3. Now you plug into the formula. So this one, like at the back of the quiz or on the last page of the test or something like that, I'll have all these formulas there, and you'll just plug into this one. This one again starts at x0, goes all the way to the n, but it starts at a 4 and it alternates 4, 2, 4, 2, 4, 2. So, and it has a delta x over 3. So we know S4 is going to be delta x over 3 times f of 0 plus 4 times f of pi over 4 plus 2 times f of pi over 2 plus 4 times f of 3 pi over 4 plus f of pi. This would give us pi over 12 times sine of 0 plus 4 sine pi over 4 plus 2 sine pi over 2 plus 4 sine 3 pi over 4 plus sine of pi. These guys and these guys are 0, so this just becomes pi over 12. Pi over 4 is radical 2 over 2, so that's just 2 radical 2. Sine of pi over 2 is 1. Sine 3 pi over 4 is also 2 radical 2. So that becomes pi over 6 times 1 plus 2 radical 2. And that would be the approximation according to Simpson's rule. So you do those calculations, plug into the formula. Okay, find the associated errors with the approximations that you did in problem 1. So we found an approximation to this integral using 3 different methods, the midpoint rule, trapezoid rule, and Simpson's rule. Now the question is, how good are these approximations? Turns out you can prove that this measures how good the approximations are, and so we're going to use it. Any questions on this? I mean, it's really the same idea behind a finite Riemann sum or a finite left-hand rule or right-hand rule that you've done before. But we're just introducing pretty much 2 different ways because you already saw the midpoint rule. But let's actually see how good these guys are. So we're gonna compare them. So this is problem 2 on the handout. Now we want, what is the error for the midpoint rule, the error for the trapezoid rule, the error for the Simpson rule in problem 1. So first let's do the midpoint. So you look at that rule that we have here. It's k times b minus a cubed over 24 squared. Right. And you'll see here, the k is kind of weird. That's something you have to figure out. But you'll notice here I gave you the rule for figuring out what the k's are. The k in this case is a constant such that it's always larger than the second derivative. Right? So I can prove that if you pick any number larger than the second derivative, this guy will work. So the goal would of course be try to pick the smallest number that's larger than the second derivative, and that's giving you the best way to measure the error. So here k is a constant. So this one would require a little bit of work here. The rest is just minus plugged into the formula. Right, and any constant would work. Finding the smallest such constant is best. But of course, if you find a constant that's less than that, that's bad. That means it won't work. Let's look at how to actually do that. So this would be the error for the midpoint rule. So when you're finding error, step 1 would be to, of course, find the second derivative, because we're going to use it. So we're going to find, so our f of x is sine x, that was our original function, which means f prime is going to be cosine x, so that f double prime would be again be sine x. So that's the first step that you do here. Second step, to find an appropriate k. Right. Technically it should work on this integral, but for this function it's actually going to be nice on the interval. So here we want, in other words, our k to be greater than or equal to the magnitude of sine x on the interval 0 to pi. But we kind of actually know what such a constant is, right? What's the smallest constant you can think of that's always greater than a sine function? Greater than or equal to? There's actually a best choice here, which is not very often. 1. Sine is literally always less than or equal to 1.
Oh, right.
Choose k equals 1. That's going to work here. So in this formula, I'm going to go and I'm going to plug in the pieces. I'm going to plug in my k equals 1, my b equals pi, my a equals 0, my n equals 4. And that's actually going to tell me how good this approximation is. It's at least this good. So that's 3 plugged into error formula. So this means the error associated with E4 in this problem will be given by 1 times pi minus 0 cubed over 24 times 4 squared. So that's just pi cubed over 24 times 4 squared. What is that roughly? You guys play in a calculator, let me know roughly what that is.
0.0807.
0.0807.
Yeah, do you want
Okay.
more?
So, no, that's fine. So, one thing I want to do, I'm not going to do it, but one thing I'd like you to do is to actually try this. Actually compute, compute the integral from 0 to pi of sine x dx. You can actually do that. What is that going to be? Is that like 2 or something?
It's cubed.
It's like 2. Right, so that was easy. Right? So do that, and then the answer that we got for the first one, which I didn't actually write that out, then find M4 in your calculator. Right, that 2 things, and compare the answers. Now, according to this theory, the answer should be within 0.08 of 2.
Yeah, do you want that?
Well, I don't know. That's for you to check. Because this is not always something you're going to do. This happens to be a very nice integral. Like in general, I'm going to give you for an integral that's really nasty, and you wouldn't be able to do this anyway. But it's just for fun. I'm not going to actually do that. In a problem, if I were giving a problem like on a test or a quiz, I wouldn't have you do all the rules, like do the midpoint, blah, blah, blah. I'll do one rule. I'll pick a rule at random. Here's an integral. Use Simpson's rule to approximate it with 4 subintervals. Tell me how good your approximation is. That would be like a fully contained problem. So it'll be something like that. Right? And I might also ask a problem like problem 3 as well as a follow-up. How many subintervals would you need to make sure your error is this good? Right? So that's something else we can determine. Right? But you can actually try this. You can even try it with all 3. Right? Use the error formula for the Simpson's rule and Trapezoid rule and actually try them. See how close you get to 2. Right? Who's going to be the best approximation? Let's do the errors for the other ones here as well. I think we can probably talk about problem 3, that would be nice. Okay, so we're now at B. We're looking for the error approximation with respect to t. We know that that's going to be k times b minus a cubed. This one is over 12n squared. And again, where k is less than or equal to the magnitude of the second derivative on the interval AB. Yes.
I'm just a little confused as to how, like something like Trapezoid Rule or Simpson's won't just like always be better than the right-hand rule or the left-hand rule.
But why it won't always be better?
Yeah.
Well, it depends, really.
Okay.
I mean, you can draw, I mean, the shapes that I drew last time kind of said, well, sure, if my shape was like this, then yeah, you can always say something like the trapezoid rule would be better.
Right.
But your functions can have really nasty shapes where
Okay.
it's just a trapezoid, fitting a trapezoid in these crevices is just not as efficient as fitting a rectangle in these crevices, right? I could have a function that was literally like, you know, like straight lines stacked on top of each other, and a rectangle would always be better than a trapezoid. So it really depends on the situation. So the pictures I graphed might suggest otherwise, but in general, you can have your function doing all sorts of crazy things. It's just that sometimes some shapes are nicer to fit into certain crevices than other shapes. Ultimately, they'll both tend towards the answer the more of these shapes you use. And if you take an infinite number of them, they'll all converge to the same answer, but some will converge faster. Right? Some you'll need less shapes to fit everything in. So here, the first thing we're going to do is find our second derivative. So sine x is this. We already found that f double prime is minus sine x. 2, we're going to find k. So again, here. So I'm choosing a nice function with nice numbers for our first example. In the book, you'll have a little bit more trouble finding these guys. Since 1 is greater than well, that's always true, but it's in particular it's true on the interval 0 to pi. So 3, plug into formula. This will mean that the error associated with your trapezoid rule will be less than or equal to 1 times pi minus 0 cubed over 12 times 4 squared. What's that roughly? Pi cubed over 12 times 4 squared?
Oh, 1.5939.
1.59?
Yeah. Because if you think about it, that's like 30, oh wait, no, I had it too high.
0.161.
Yeah.
Yes, thank you. I had pi over 5, pi to the 5th, sorry.
1.69?
0.1615.
0.1615. So for the sine, the trapezoid rule was actually worse than the midpoint rule. So for this particular function, the trapezoid wasn't as efficient. Right? To get closer to the answer, I would need more than 4 trapezoids to get that good. Let's quickly find ES. This one, yeah,
So the trapezoid was worse than the midpoint?
yes.
Why, when it's greater than what the midpoint was?
This is the error.
Oh.
This is how much you're wrong by. Right? When you're measuring the error, that's how much you're off by. So I'm actually off by more, so that's why it's worse. The number's bigger, but bigger isn't always better. It is in Texas, so. Yeah, so that's how much you're wrong by. So it turns out that with 4 trapezoids, I got a worse approximation than with 4 rectangles at the midpoint. ES is a little worse. You have to go through like 4 derivatives, but I think that would just end up with a positive sign, right?
Yeah.
Yeah, you'll just end up with a positive sign. So this guy's a little bit more complicated. And to the 4th. Such that k is greater than or equal to the magnitude of the 4th derivative on the interval. Well, for this problem, it's nice. K is again 1 can work. So 1. We're going to find f to the 4th prime. F equals sine. F prime is cosine. F double prime is minus sine. F triple prime is minus cosine. F 4th prime is positive sine. 2, find k. So I want k to be greater than or equal to the magnitude of sine on this interval. Turns out that 1 works. You could choose any number bigger than 1, but your error would be too big. You kind of want to make your error kind of don't want the cushion to be too big. Because if this is something that you're choosing, for example, to determine how much of a resource you're going to buy, and you say, well, we might be off by this much, you don't want to force the supplier to buy, force your person to buy more from the supplier than they'll actually ever need. So it's nice to kind of minimize the error as well. So you sort of pick the best number you can pick here. Don't just pick, oh yeah, k is 1,000,000. And sure, yeah, I'm not going to be off by 1,000,000 by taking 4 rectangles, that's clear. But, you know, you want it to be as nice as possible. So here, I would say my error according to the Simpson's rule for this particular function is going to be 1 times pi minus 0 to the 5th over 180 to the 4th. Plug in n equals 4, so that's roughly what?
0.0066. I checked.
0.0066.
66. Yeah.
Okay, so it turns out we can make a conclusion here. For this integral, 0 to sine x dx, with n equals 4, Simpson's obviously gives the best approximation. So that number we got by doing Simpson's rule, it's actually going to be off by 2, off from 2 by 0.006. So that answer will be somewhere between 2.006 and 2 minus 0.006. So that's the error. That's how much you're wrong by using these approximations. Sometimes, so here I gave you the number of approximations and we can compute how much we're wrong by, but sometimes I might want to require you to give me an answer that's within a certain tolerance. So I might choose ahead of time, whatever answer you give me, I don't want it to be off by more than 0.001. I could say that to you. How would you know how many subintervals you need to cut it into with a particular rule in order to achieve that? So that's what problem 3 is about. And that's also something I'll ask you. So look at problem 3. So here we're considering 1 to 2 of 1 over x. Again, an easy integral you can do. We want the error to be less than 1 over 100 using Trapezoid Rule. And what I'm asking is, what must n be? How many trapezoids do I need to be that close to the actual answer? Right? Now if you want to do that, it means if you don't know the n, you can use the error formula and actually solve for the n. So we know for the trapezoid rule, the error according to trapezoid rule is less than what? What was this, 12n squared? So we know that's true. That's how my error is going to be. So the question is, how do I choose an n so that the error is less than 1/100. What would you do?
Find K. And then set it equal to 1/100 and then solve for n.
Set it less than or equal to
Oh,
1/100, right? So you want to set basically k times b minus a cubed over 12n squared to be less than or equal to 1/100, right? That's what you want. I want the error to be less than that number. So again, the n we don't know yet, that's what the question is asking you, but we do need to find k. So you start with the function, which is 1/x, or I can think of that as x to the minus 1. Find this first derivative, find the second derivative. So this is 2/x to the cubed. So we want k to be greater than or equal to the magnitude of 2/x cubed on this interval 1, 2. Can you tell me such a number? What's the largest possible value of this function on that interval? 2. It's actually 2, right? Notice that choose k equals 2 here. Why? Because this guy is a decreasing function, right? If I look at 2/x cubed, the graph is going to look like this, right? It's going to be decreasing. So clearly its largest value happens, its biggest value is going to happen at the 1. It's going to happen at this corner. So knowing about the function is going to help you, right? So that's going to be the largest value, and it's 2 at that value. And it keeps decreasing otherwise. So for this particular function, its largest value happens at the left endpoint, right? If you needed to do, in general, what you could do is you could just do calculus, right? If this function is something you don't really know what the graph looks like, differentiate it, set the derivative equal to 0, solve for the critical points, find the maximum point, make sure your k is bigger than that maximum point. Here k equals 2 works. So now what that means is, this implies we want 2 times 2 minus 1 cubed, because that's the right endpoint, left endpoint, over 12n squared to be less than 1/100. 2 minus 1 is just 1, so this is basically me saying 1/6n squared. I want that to be less than 1/100. This is the same as me saying 6n squared to be greater than or equal to 100. So this is
2 on top, e times 2.
Huh?
2 minus 1 is 1, 2.
I canceled. 2 into 12 goes 6. And that's 1. Okay, so this basically says my n should be greater than, of course my n is positive, it's going to be a number of rectangles that I'm looking for. It's going to be 100/6 and take the square root. What is this roughly?
4.08.
4.08. So basically choose n equals 5 to get an approximation this good.
Why not 4?
Because 4 is not enough. Right? I need a
Oh,
little
yeah.
more than 4, but n has to be an integer, so I have to round up to the next
yeah, I
highest
see.
one. So you can kind of know ahead of time. If you know you want to use this rule and you have a certain function, you can actually figure out how many subintervals you need to get an answer within some tolerance. So I can know ahead of time. If I'm using trapezoid rule to approximate this to be that far away from the answer, at most, I need to choose 5 subintervals. We'll stop there. That pretty much covers the topic, so we can have the homework for that due on Tuesday. Problem 4 you can find. But as I said, in general, if I'm giving you a test or a quiz, I would have like one integral at the top, and it would have parts to it, and I'll say in part A, use Simpson's rule with 4 subintervals to compute, approximate this area. Find the error of your approximation, and then I can ask, what if I wanted the error to be less than 0.01, what would n have to be? Right, so that would be like one question.
Then we have to, you're saying that we don't have to memorize the formulas, or?
As the formulas here and the error formulas, you don't have to memorize. I will give them to you. But you do need to know how to use them, what to do first, what to do second. And there's a little bit of algebra that happens here. That's it.